Now to explain a bit better the four component parts of a typical makeup graph for a threaded and coupled shoulder connection. So we'll show this animation here, and you can see a connection being assembled, and you can also see the build path. And what you see here is what was described previously. We have from zero a smooth thread interference build up to this point here, and then after this it's thread and seal, because at about this point here approximately, I mean it's not an exact science, the seal is starting to come into contact. So from this point onwards you've got thread interference and you've actually got seal interference combined, and that's why it builds to this point here. Within this build slope you need no irregular discontinuities. It needs to be a fairly smooth gradual build process. That's how this type of connection works. There are other graphs and other types of connections which will work differently, but this one, which is a fairly standard, most commonly used type of connection, which is threaded and coupled shoulder connection, will have this type of build slope. A thread part and then a thread and seal part. Once we get to this point here, that's called the torque shoulder. That in effect is when these two surfaces meet, which is the shoulder. And as you can see, there needs to be, as explained before, there needs to be a distinct change in direction at that point. That's the torque stop, the shoulder point. That's where these two surfaces have met and minimal rotation can happen any further. So you're putting a lot of force for very little movement. Hence the reason there's a positive identifiable shoulder point which must fall within certain parameters. Now there's a minimum shoulder torque point, as you can see here, and then there's a maximum shoulder torque, and the shoulder point must be within those two parameters. So there's a minimum and a maximum. It can be anywhere in there, but it has to be in there, and that's part of the manufacturer's criteria for makeup. So we get the shoulder point here, and then after that we build. So if we run this animation on, you can actually see the third component part, which is your delta torque build. And the delta torque build is all the torque that's been applied to the connection after shoulder point. It's actually stopped rotating now. You're actually applying force to a connection that's not willing to move. Hence the reason it's an exponential linear direction that the graph takes. Now, the experienced specialist can translate all this into what's happening in here, and that's why the person interpreting the graphs must understand the connection and must understand the design and the connection mechanics and how that connection in each individual part interacts with the corresponding part in the box connection. So at any given point within this build slope and within this delta torque build, the individual knows exactly where this connection is in its assembly process. So back to the graph, we've reached shoulder torque and it's within parameters. We've then got our linear build to final makeup torque, and as you can see there's a minimum, a maximum, and as discussed this one's actually hit just above optimum torque, which is the perfect place to be finishing with the torque application. Thereafter, this is just the drop off where there's no torque being applied after that. This part here, from the shoulder point to this straight vertical line, this part in here is called the delta turns. That part there indicates to us how much rotation the connection has actually has occurred in the connection after shoulder point, and it must be minimal. It must be minimal for obvious reasons. It's actually hit a positive barrier. The shoulders have come into contact. It can't rotate too much more, so this must be actually quite small. That's that. So this whole thing, the component parts plus the whole picture, needs to be analysed by a specialist. Now, if it's not a specialist analysing this, inexperienced people looking at this won't know how to interpret it. Why? because they don't know the design of this connection. So they don't know at any given time where that connection is in its makeup process. If the wrong graph is accepted and run in the hole, that actually means either a damaged connection or an incorrectly made up connection is being run in the well. This results in problems. It can result in an immediate leak, or it can result in that connection in service eventually creating a leak within itself, simply because the preload process, and that's what this is called, makeup is preloading the connection with energy, has not been completed as the manufacturer states it should. That's why you need a specialist to actually interpret these graphs. Not just anybody can do it.